Hello everyone, in this video we are going to look at two groups of chemicals that look very similar to the alcohol and the ether. The first group is called thiol. So in thiol you have a sp3 sulfur connect to hydrogen, and the other side connect to a carbon that is sp3 carbon. So most of the time you will see a R group connect to SH, that is a thiol. For example, if we are looking at the CH3CH2, the ethyl group connect to SH, this is sp3 carbon here, right? And for this one, what we call it is ethane, right? This is 1 to 2 carbons, and put the name thiol. And another way to name thiol is that we consider SH, this group, as the substituent. So when it's a substituent and have a very special name, it's called mercaptan group. So for the ethane thiol, we can also call it as one mercaptan ethane. And another example here, if we put this thiol, for example, onto a cyclopentane, so SH as a substituent, we call it a capital cyclopentane. So that is a thiol. So when we are talking about thiol, the physical property of thiol is that they're very stinky, and because this is sulfur inside. One example is the smell comes from the natural gas. For natural gas, it is the methane, right? Methane actually don't smell. The smell actually comes from the methane thiol that's added into the natural gas. Why is that? If there is a natural gas leaking, if you only have the methane inside, you will not know because you cannot smell it. It's stinkiness. However, if you have the methane thiol added, if there is a natural gas leaking, you can smell it right away. If we are looking at thiols, and we know that thiol is a strong nucleophile. The reason why is you do have these lone pairs on the sulfur, right, can attack the electrophilic center, so it makes a strong nucleophile, and it is a weak base. Why is a weak base? Think about the size of the sulfur compared to the oxygen. Sulfur is much bigger. Even then, in the same group, thiol has the extra shell of the electrons that is much bigger, and that means the thiol can be more polarizable, that can stabilize the electrons much better. So that make the thiol is a weak base. And also, if we deprotonate the thiol, you will have this negative charge. And the same reason, that negative charge is very well stabilized by the sulfur. So that make even the conjugated base, it is a weak base, but a strong nucleophile. If we are looking at the acidity of thiol compared to the alcohol, thiol is more acidic. The pKa value of thiol is about 8, and the pKa value of alcohol start with 16. Okay, so what does that mean? That means the conjugated base, right? Conjugated base we are looking at here. This one will be more stable, and we already explained that because sulfur is more polarizable and stabilize that negative charge better than the oxygen. So if we want to make thiol, deprotonate thiol, now if we are introduced, for example, sodium hydroxide, what happens here is it will deprotonate it, and we'll have the conjugated base right here, plus water, of course, and sodium ion. And in this case, pKa value of water is 15.7, and pKa of thiol about 8, and this reaction totally happens and favor to the right side. That means sodium hydroxide now is basic enough to deprotonate thiols, to make it a even stronger nucleophile because that negative charge here. Next, we want to look at how to prepare thiol. So what we can do here, if we are introduce a alkyl halide, for example, this propyl bromide, that we introduce a strong nucleophile, then that will undergo the SN2 reaction mechanism, right? This is going here, kick this off, SN2 reaction mechanism, that you will replace the bromide with thiol, more capital group, and that give you the thiol. And if this good leaving group is on a tertiary carbon, what will happen here is it will be a SN1 reaction mechanism, and you will have a more capital group connected to a tertiary carbon. So that is SN1 reaction mechanism. And we are looking at the reaction of thiols. Because they are strong nucleophile, what we are looking at here is substitution reaction. For example, if we start with our propane thiol example, okay, and we react this with, we introduce a primary alkyl halide. So what we get here is thiol 1, 2, 3, 1, 2, 3. We'll get this product, and this product is called sulfide. Okay, so let's look at this reaction mechanism right here. It's basically a SN2 reaction. So you have your first step, the strong nucleophile attack, and at the same time the leaving group leaves. So what you have here is SH, and you will have that positive charge, 1, 2, 3, 1, 2, 3. Okay, you will have this as the intermediate, and then you need to deprotonate this hydrogen. So most of the time you have this bromide, right? It will grab this hydrogen, and let me change another color, grab this hydrogen and give you the final product. That is through the SN2 reaction mechanism. So if you have your thiol that is propane thiol, and then we react with the third butyl bromide, then this will be a SN1 reaction mechanism. And what we will have here is third butyl group right here. And let's look at the reaction mechanism here. So first of all, the leaving group leaves, that will give you a tertiary carbocation. And then let's see, this step 1, this is step 1, right? And then step 2, your strong nucleophile comes in, and here you need to think about stereochemistry, right? For this carbon is not carcinogenic, so it really doesn't matter. And what you have, 1, 2, 3 sulfur, and then you will have this. And then the last step, again, right, it needs to be deprotonated to form the final product. And so that is a step 3, and this is the SN1 reaction mechanism. So thiol can work as a strong nucleophile for the substitution reactions. And the products from previous page that we basically connect two alkyl group to the sulfur, and that gives us the second group of chemical compound. It's called sulfide. And in general chemistry, you may already learn this hydrogen sulfide, which is a stinky gas that released when the egg went rotten. That is a smell. And sulfide here is when the sulfur connect to two alkyl group. In other words, connect to two carbons that are sp3 carbons. So it's connect to sp3 carbons. For example, if these two R group that are the same, if we introduce the SO groups, so this is called diazo sulfide. It's just like the ether, right? If you have the oxygen instead of sulfur, you have diethyl ether. And basically what you need to do here is give the name of the substituent. For example, let's do another example here. If you have butyl group and then you have a propyl group, then butyl goes first, then you have a butyl. Propyl sulfide. Okay. So one skill here is that if you are given the name of this compound, you need to be able to draw it out. So how to prepare sulfide? Preparation of sulfide. Well, I see that we will start with thiol and we'll run a substitution reaction to prepare the sulfide. For example, if we start with thiol, and usually we will introduce a strong enough base to deprotonate it to make a thiolate. And this thiolate is a thiolate. And then we will introduce a alkyl halide. For example, this halide, a good living group, right? Good living group with an alkyl halide. Then we know that this will undergo the SN2 reaction mechanism that will give you the product, which on one side you have 2 carbon ethyl, the other side you have 3 carbon propyl, so ethyl propyl sulfide. And if you write this reaction all together, so from center right side, basically step 1, right, you introduce the basic enough base sodium hydroxide to deprotonate to make a even stronger nucleophile thiolate, and then introduce a primary alkyl halide. And here also you can have secondary alkyl halide. It also will undergo the SN2 reaction mechanism. However, if you introduce a tertiary alkyl halide, then it will undergo the SN1 reaction mechanism. And for sulfide, there are a few very interesting reactions. So the first reaction is when you oxidize thiol, and that will go to make a disulfide. What is disulfide? So basically what we are having here is, this is called disulfide bond. It will connect to something else. Okay, this is disulfide bond. It's very useful in biochemistry to create this disulfide bond, and this bond is very active, then you can break it down. Okay, so what happened here is, if you have, for example, this SN sulfide and with another SN sulfide, and then you introduce a either bromine or iodine, and usually you will also have a base right here, and what you will have is you will create this disulfide bond. Okay, And the reaction mechanism look like this. If you start with your base, you do need that base, and this base first will deprotonate it to create the thiolate. And then, for example, we're using bromine here. The bromine is staying here and will participate in the second step. You will have this, grab one of the bromine, and second step, you will form the sulfur bromine bond, okay, and also with the bromide from second step. And the third step, you have another one equivalent of this thiolate, and that is a strong nucleophile. Now here, what we have is, we know that the bromine is electronegative, so it pulls the electron density away from sulfur. So that makes the sulfur a electrophilic center. So that will be good for the nucleophile come in, attack it, and kick off the leaving group. So that is actually kind of an SN2 reaction mechanism that form our product right here. Right, that will give our disulfide bond. Okay, and also you will have bromide floating around. So that is oxidation of thiols to form a disulfide. And another reaction here is this disulfide bond can be reduced back to the thiol. So let's start from here. Okay, if this is our starting material, disulfide, what we can do is we will do a reduction reaction. So here the reagent is, you will introduce zinc and HCl, and basically what we will do is we will reduce it back to thiol. So here from thiols to disulfide, that is an oxidation reaction. And from the disulfide bond to the thiol, that is a reduction reaction. So that is thiols and sulfide. I will see you in class.